Thanks, David. Thanks for having me back. I really enjoy coming up here and talking at the observatory. David did mention that I work for NASA, but I have to give the caveat that I'm not here representing NASA tonight. I'm actually here for a planning meeting for an activity that I'll talk about at the end of the talk. It's called the Tennessee Valley Interstellar Workshop. And so I'm kind of speaking as a private citizen tonight and not representing NASA. So any opinions I give that may or may not fall along what the current plans are strictly my own. So I have to give that caveat. The Stars My Destination is the topic that I chose to call this tonight. But it's really a talk about the recent discoveries in extrasolar planet research, which is causing a lot of people to ask the question, well, we're finding these possible other worlds. How do we ever get there to them? Can we go to the stars? And I get that question a lot. So much so, in fact, that it's the topic of a collection of science fiction short stories and essays about interstellar travel that I put together. And I'll talk a little bit about that also later in the talk today. But the main thing I want to give tonight is a status of where we are in extrasolar planet research. What's been found, how many are out there, kind of a little bit about the techniques, which some of you all probably know a lot better than I do, being astronomers, teaching astronomy. So hold any corrections until over, okay? Don't trip me up here. But I'll take any questions from the audience anytime. I like talking to folks. So if you have a question, just stop me. I'll be glad to rewind and go over that. I'll talk about methods that we might use to go to the stars, things that don't require new physics, things that the current understanding of the way that nature works might actually allow us to go to the stars sometime in the future. And then we can have some Q&A, and you can ask whatever you want about the presentation, about space exploration or otherwise. I like to talk with folks. So if you want to hit the lights, I'll go ahead and get started.
Thanks, Les.
I picked this title because I remember a great book by, anybody remember the author of this book?
Yeah.
Who?
You.
No. Alfred Bester, classic science fiction novel, written back in the golden age of science fiction, back in the 1950s, I believe. And I picked the title of my talk based on this book without having really remembered what the book was about. And once I started thumbing back through the book and realized it was a very dystopic, depressing book, I probably shouldn't have picked it for the talk title. But I do recommend it because it is kind of the view of what the future would be like from the way people viewed the world at the time it was written. If you read a lot of old science fiction from the viewpoint of today, you've got to kind of put yourself back in the Cold War, post-World War II way of thinking about things, and it's really interesting to see how they thought of the future versus the way we do today. So I do recommend the book. It is a little depressing, but it's actually a very well-written book. Back a year ago, January of 2013, National Geographic did their 125th anniversary issue on exploration. They interviewed explorers from all over the world about exploration, and they wanted to do one of the stories in here about interstellar exploration. There's been a lot of talk about going to the stars. The results from the Kepler Space Telescope are coming in. We're finding planets out there. People are asking, can we go to the stars? So they came to NASA, they interviewed people all over and asked a lot of questions about going to the stars. Well, it turns out in their 125th anniversary issue about great exploration, they actually picked the Interstellar Voyage as the cover article for that issue of National Geographic. And I was very honored to have my picture appear in National Geographic, and I felt very guilty at the same time. I'm the interstellar explorer for that issue. All the other explorers are people who are climbing mountains in the Himalayas, have their feet get frostbite, lose toes. Another explorer is one that's exploring in the jungles of Latin America, and he's had malaria. The worst I have to worry about is getting sunburned out there holding this material. And the material I'm holding in the picture is a piece of a solar sail. Now, I gave a talk on solar sailing here. Was anybody at that talk? Do anybody remember it? Solar sails are a way to travel through space using reflected sunlight. Well, it turns out that since I last spoke here, and I'll talk more about solar sails a little bit later on, there have been 2 new missions selected to fly using solar sails. And they are being managed out of the Marshall Center and are going to fly in 2017. So there are now 3 NASA missions using solar sails planned in the next few years. And I'll have more of that in the talk because that's my favorite approach for going to the stars. So I was very honored to be in this issue. And for me, it was way cool that interstellar exploration is the exploration they chose to put on the cover as what is the future of exploration, space exploration. Now, why am I here? And why do I do what I do? And what motivates me to think about going to the stars? Well, like a lot of you, you're probably Star Trek fans, all right? Star Trek was a great motivator to people of my generation. If you work at NASA, there was a survey done where they surveyed NASA employees and said, what motivates you? Why are you here? And they did a plurality of what words people mentioned. Well, the number one word that people mentioned the most when they were asked, why do you want to work for NASA, was the word exploration. The next most common two words were Star Trek. Okay? So it was kind of interesting to see that this is the words that people utter when they talk about why they work for NASA. Of course, in terms of being inspired by science fiction, it was more than just Star Trek. I started reading science fiction. I started thinking about going to the stars. Some of the great classic science fiction spaceships are on this slide. Some serious, some not so serious.
Wait.
Oh,
That's a distinction?
Yeah, you got to make a distinction. Some shows take space travel seriously. In all seriousness, if you want to see shows that really take it seriously and kind of postulate what I think is a realistic field of future space travel, aside from 2001, you've got to watch Babylon 5.
Yeah.
Okay, I really believe that. If you just want to have a fun ride, of course, these two in the middle here, Buckaroo Banzai, as well as Douglas Adams' Hitchhiker's Guide to the Galaxy. But I was also inspired by science fact. I remember as a very young child watching the Apollo 11 landings. There's a gentleman here who said he was on the Apollo 8 recovery crew. So, I mean, that was an inspirational thing. It inspired a country, it inspired a generation, and many people thereafter to be interested in space. But you know, it's not just space exploration in the nearby neighborhood. It's this great universe we have out there. I think it just calls to you. Just tonight, if you came in and you saw Jupiter and the four moons, you're into astronomy, you obviously know what I'm talking about. It's a calling. To me, I go look at a starry night and it's almost like there's something empty in here unless I'm looking at the stars. And that's important. But what's astounding is that before 1992, we didn't know there were any planets other than the planets in our solar system. So this whole notion of a landing party finding a Class M planet and exploring was just in science fiction. There was no scientific evidence that there were any planets out there other than those circling our star prior to 1992. Okay? So, wow. Think about the textbooks being rewritten in most of our lifetimes here. Okay? A lot has happened. What happened in the early 90s was the first confirmed extrasolar planet. Typically, these were very extreme planets, very large planets, because in order to see their effects on their parent star or whatever it is they were orbiting, they had to be really big to have an impact. And the first confirmed extrasolar planet, as my understanding, was a pulsar, a planet circling a pulsar. And pulsars are very regular in their radiation emissions, and there was an irregularity that was eventually determined to be caused by something very large in the neighborhood orbiting it. Well, since then, the techniques have become refined in order to detect extrasolar planets. And not only are we finding them around extreme objects like pulsars, but we're finding planets around stars like our own sun. We're finding planets that are in the Goldilocks zones, not too hot, not too cold, could conceivably be orbits that have liquid water and are stable and seem to maybe have the conditions for life from what we can tell from afar. These are still, in large part, a lot of the planets that are found are very extreme circumstances, very close to their parent star, typically very large planets, but we're finding more and more smaller planets in more hospitable places as the number of extrasolar planet counting continues to go up. And the numbers are pretty amazing. I haven't had time to correct the wording on this chart. I looked up again as of January 14th, and it's my understanding the confirmed number of exoplanets today is now over 1,000. And I want to point out that there have been more candidate exoplanets detected than that. But in order to be a confirmed exoplanet, it needs to be independently verified by a separate measurement technique. So if you think of all the ones that have been seen by the Kepler telescope, where it's looking at the brightening and dimming of stars by the planets passing in the line of sight and dropping the light output of the star, until those are verified by some independent group with an independent technique, it doesn't officially get counted as a confirmed exoplanet. So the numbers you hear, and I see a Kepler poster up here, is you're going to hear numbers well into the multiple thousands of exoplanets, but those have yet to be a lot of those have yet to be independently confirmed, and these numbers are just going to go up. What's way interesting for that is if you look at this model of the galaxy, all of the confirmed exoplanets are in a very small region near our star within the Milky Way. So when we're looking out there and we're seeing these thousands of confirmed planets, we're looking at a very small local neighborhood in terms of what we're able to see, which is good, because the methods of interstellar travel that I'll be talking about this evening are not going to get us across the galaxy. We'll be lucky if they get us to the closest stars. But at least we can explore some of these nearby stars and maybe see some planets other than those that form around our star. Based on this sampling where we are right there, the latest estimates are that there are between 100 and 400 billion exoplanets in the Milky Way. And that number is likely to go up. That estimate, because from what I'm hearing is that some of the stars that they originally thought they would not be likely to find planets around, they're finding them there. Double stars, places that we might not think we'd have a stable gravitationally bound planets are actually being found around some of these stars. So that number is going up. Now there are different methods by which we can find exoplanets. One of the simplest to understand that is in wide use, and this is not what Kepler is doing, but just like the sun, which is very massive, keeps the Earth in orbit by gravity and the gravitational attraction between our sun and the Earth's also pulling on the sun, right? And it turns out that the sun actually, and a star with a planet going around it, actually, when it's facing it, they actually pull on each other, and we induce a little bit of a wobble in the star, okay? Well, the light that's coming out from the star, if it's being pulled toward us a little bit, is going to have a Doppler shift, just like with a train passing. And until the last 20 years or so, we didn't have instruments that were sensitive enough to measure this Doppler shift, but you can actually measure that. And if you have a regular Doppler shift in the light from the star that occurs on a regular interval, there's something periodic happening. And you can figure out what that period is, and it's a planet. And you can, from that, determine basically its orbital distance, and you can infer things about that planet. So we are detecting stars from planets around stars from some very, very faint signals that were just not possible to detect many years ago. And a lot of that's being done on the ground today, as well as in space. How else can we find exoplanets? Well, the transit method, which is the method that Kepler uses, is basically like going out at night, turning on your bright headlights, staring at them, and being able to see when a mosquito flies in front of your headlight beam, right? It's really hard to see. Stars are really, really bright. Planets are not so bright because they're reflecting light of the star, or in this case, blocking a little bit of light from the star. But we're getting really, really good at counting photons now and counting light. So we have very sensitive detectors that are able to detect very small fractional dimming in the light from a star as the planet passes between us in the line of sight between us and that star. And that's another method you can use to determine if there's something moving around that star. And that is the method that the Kepler is using. There are other methods that I won't go into. One fun one, this is microlensing, but I really think that gravity lensing is going to be one of the excuses we use to send probes into nearby interstellar space, not too far in the future. Because this is an astronomy group. You're familiar with an Einstein cross. Who knows Einstein crosses, right? Okay, basically, according to special relativity, light is constrained to move through space-time, and mass can bend space-time. All right? So light will bend around a massive object because space-time is bent around that object, and light has to move through space-time, so it too is going to be bent. Well, what else bends light? Right? Optics, refraction. In your glasses, in your eyeball, it's how you focus. So a heavy, massive object like the black holes at the center of galaxies will bend the light from distant objects on the other side of those galaxies, and if you're in the right place, that bent light will be at a focus, and if you're at the focus, you can see things you ordinarily couldn't see. All right, well, it turns out our sun is not a million-mass black hole, but it is pretty darn big, and it does bend space-time. Turns out the gravitational focus for our sun is at about 500 astronomical units. So 500 times 93 million miles, the Earth's sun distance, you can get out there, and there is a focus for the sun, its gravity lens point. So if we were to put a telescope out there, we could take advantage of the sun as a primary optic and use that for doing astronomy of things that are pretty far away. Been a lot of papers written about this, some books written on it. A fellow who comes to our interstellar workshops is an expert on gravity lens missions. His name's Claudio Macconi. And I encourage you to look up some of his work in published literature, because I think For astronomy, that's going to be one of the stretch goals for the next generation, is to get a telescope out to 550 astronomical units. There are people who are cataloging these exoplanets. Johns Hopkins University, if I'm not mistaken, is maintaining an exoplanet, a habitable exoplanet database, where they look at what kind of stars are these planets orbiting, how big are the planets, are they in the Goldilocks zone, are they in stable orbits, and how Earth-like are they. They come up with an index to try to measure these planets and determine how similar they might be to the Earth based on these characteristics that we're able to observe from afar. We're not to the point yet where we can do spectroscopy of their atmospheres or use a gravity-lensed Hubble Space Telescope to see if there are city lights at night, which would be ultimately trying to find out what's out there. But they are coming up with this index, and they're going through the discovered exoplanets and kind of giving them a rating as to how similar to Earth they might be. And I won't go into that rating system, but they have found some that get close to a 1, and 1 would be another Earth. Yeah.
Just for clarification, those images of the planets are fake.
Oh yeah, these are all
Just to make
artwork,
sure. Yeah.
fancy artwork. But the names of the planets here are not. And those are their habitability numbers. And these numbers are changing. This is an updating, evolving database. I'm sure it involves lots of graduate students to update, and they keep updating it regularly.
Les,
Yeah.
4 of those 6 are Gliese. Is that a constellation name there that all those things are in? Because 2 of them are in the same star system, it looks like.
You know, I'm not sure I know the answer. Does somebody in here know about that? Anybody know about that star system?
It seems mighty interesting because like the 581,
Yep.
the first and the last one, 581G and D, those are same planets around the same star.
You would
right?
think, yeah, yeah. And
That's
very interesting.
that-
That's a good point. I hadn't.
Yeah, those that must be an on-axis. That must just be one of those. The ecliptic of its system must intersect the
Yeah, some
sun.
of them, we know about 9 planets around the same star.
Well, no, but I
Some
mean
of
2
them.
habitable ones around the same star means
Yeah.
that there's an occlusion event that allows us to detect all of those planets.
Well, and if someone were looking in toward our solar system, they might put Venus in that, pretty high habitability index, I would think, based if they were
Yeah,
looking
particularly if they
far.
breathe methane.
So, well, yeah, but they haven't done spectroscopy. And the nearest known extrasolar planet's right next door, right? The nearest star system, the Centauri, Alpha Centauri, Proxima Centauri system. Alpha Centauri B has a planet. So the nearest one
At
we
least
found
one
is,
planet.
virtually speaking, right next door. Now, this is not one I'd care to visit, right? It's very not similar to the Earth. It's a 3.3¼ day period instead of 365 days, and look how close. Very close to the star. So, I mean, it's not one that I think would be particularly fun to visit, but it's there.
Do you have the slide on this recent discovery of a very short period planet that was found?
No.
The orbital period is something like 13 hours,
Wow.
and the thing is thought to be basically its surface temperature is like somewhere between molten aluminum and molten iron. I mean, they're finding some like this is not this. You think this is extreme?
We'll let you have that.
No,
one.
no, it was something that appeared on Paul Gilster's blog a few weeks ago, and I don't remember
So
the name.
it's less of a planet and more of a layered drink.
More of a
Yeah.
hot drop, yeah.
I think the neat thing about all this is think about, well, for me, every new discovery and how these planets hold together and what they're like is just another realm of exploration for learning more about the universe.
Yeah, absolutely.
And it's just incredible at the variations. But this does beg the question. You know, the big holy grail of exoplanet research is finding another Earth. So, if we find it, what do we do about it? You know, how do we get there? Can we get there?
Pining for the fjords.
Well, before I answer that question, let's talk distances. Okay? The distances in space are just too much to comprehend. My brain can't wrap itself around 93 million miles. Right? It's outside of our experience base. We don't experience distances like that. And that's the Earth-Sun distance, right? So, in astronomy, they've created a unit to make that more manageable. It's 1 astronomical unit, about 93 million miles. And in the scale I'm going to create for our discussion tonight about the distance to the nearest star, we're going to do it here in this room. I'm going to call that 1 AU being 1 foot. My foot's about 12 inches long, so if the sun is right here, 1 AU is here, Earth is right up here close, Jupiter is well before I get to this front of the table here, so the planet we were looking at there earlier is real close, what, about 5 AU, so it's right in here, okay? So this is the Earth-Sun distance. If you want to go all the way out to Neptune, you get out about 30 AU. So we're back to the back row, to the wall back there in our little solar system we have in here. And it takes years for us to send a space probe out that far with chemical rockets. And we're exploring. We've flown past Neptune. We had Voyager go by Neptune. We've got a spacecraft that's going to arrive at Pluto real soon. And so we're going to be getting some data from there. And we've got these probes going out. It takes years to do it. So on this scale, 30 AU is the back of the room. How far is the nearest star? Let's drive to the other side of Knoxville on this scale. Okay? It's about 50 miles. 270,000 astronomical units. So, and I just can't imagine those kinds of distances. Okay? So here's the Earth at 1 foot. Neptune's on the back wall. Nearest star, other side of Knoxville, from where we are tonight. Pretty incredible challenge. How in the world can we do that? Well, we're not going to be in the world when we do it. And if you look further at a nearby stellar map, there are lots of interesting targets that are not terribly far away on the scale of light years. So we're not going to have a shortage of places to go if we can conquer this distance and getting across these distances. But how are we going to do that? Well, one way we aren't going to do it is chemical rockets. Chemical rockets are really good for getting a high thrust to mass off the ground. Thrust to weight rockets are great for getting mass off the ground. There are better ways. In the future, I think we'll be using to do that, but they're pretty good. But they're not very efficient. And so most of the missions where we send our spacecraft to the outer solar system, the rockets burn for 20 minutes and they coast for years to get to their destination because the rocket runs out of gas. We are building solar electric propulsion. I'll talk about that. That's a little bit more efficient, 10 times more efficient. But even that's not efficient enough to go to the stars. So poor Voyager, launched in 1977, if it were going in the right direction, would get to this exoplanet at Alpha Centauri in about 74,000 years. Okay? So rockets are clearly not the answer to going to the stars. So, how are we going to have to get there? Well, I believe we need to take a stepping stone approach. And how I got interested in interstellar research, aside from being a science fiction fan, is back in about the year 1998 to 2000. NASA got challenged to go with a stretch goal of sending a probe to 250 astronomical units within 20 years of launch. Now remember, Voyager has been flying for over 30 years and it's at about 125 astronomical units. So it's going to take about 60 years to get to this distance. So the stretch goal was come up with a way to design a spacecraft where we can study nearby interstellar space and beyond this region called the heliopause, which is basically where the outward radiation pressure of all the stars in the galaxy equals the inward radiation pressure from all the stars in the galaxy equals the radiation pressure from our sun going back out. It's basically where that's in equilibrium, okay? And for the heliophysicists, the sun physicists within NASA and astronomy, that's the end of the solar system. It's not the end of the Oort cloud. It's where the sun's influence, electromagnetic influence, drops off for them. So they were the ones who were pushing this to send a probe out there. And the reason they came up with this goal of sending this first probe within 20 years is because the scientists who are going to have the credentials and pedigree to be able to be the principal investigator on a mission of this scope, which is going to be a multi-$100 million, if not billion-dollar class mission, want to get the data back before they're dead. Okay? I'm not kidding. I was in the room with the scientists. Most of the scientists who would be of the caliber to do this mission are going to be in their 40s or 50s by the time they have the clout to be the lead scientist for a mission like this. Which means if you get the data back any more than 20 years out, they're going to be in their 70s or their 80s. Okay? And they want to get the data back and not just have it be an interesting project for their graduate students who would then be full professors or something at that time. So our goal was to get data back within that amount of time.
By the way, Peter Higgs's collaborator did not receive the Nobel Prize because he had died before the discovery of the particle. Not on an untoward concern.
Well, when we looked at the interstellar probe, first thing we did is we said, let's relook at rockets. Let's just stack stage after stage after stage and have just a heck of a time, you know, staging these rockets and having solid rocket propellant and all this other stuff. And we looked at it, can't do it. Can't get the trip time down. Can't do it with gravity assist maneuvers. Cannot get anywhere close to a 20-year trip out to that distance. So we threw that out. We found that electric propulsion might just be able to do it. Now, electric propulsion is still a rocket. You're still throwing propellant out the back so that you can move this way. Remember, a rocket is basically just me standing on a skateboard or roller skates and throwing a basketball that direction. Momentum's conserved. The momentum of the basketball going that way will be transferred to me moving this way, right? So if you have a rocket engine that has chemical fuel and it's combusting, you've got this hot gas going this way, I'll move this way just out of conservation of momentum. So if you can get the fuel to go out more efficiently, I can get a lot more total thrust. Well, using electromagnetic fields instead of chemical energy to accelerate your rocket propellant is a lot more efficient per pound of fuel than a chemical rocket. In fact, it's 10 times more efficient. And the unit that rocket scientists use to measure the efficiency of a rocket is called specific impulse, and the units are in seconds. So a chemical rocket is like 300 to 400 seconds, okay? An electric propulsion rocket is about 3,000 seconds. So you get about 10 times the total change in velocity for your spacecraft using electromagnetic energy to accelerate the propellant. Ionize it, accelerate it across an electric or magnetic field, and throw it out the back of your rocket. So we found out you could do this, but it would take a lot of power. It would take about half a megawatt of power, operating for decades, for 2 decades, to 20 years to get out there. Well, as you're going away from the sun, sunlight's not very plentiful. So how are you going to keep powering your rocket, your electric rocket? Well, the idea, Oak Ridge, was to put a nuclear reactor on board. A small fission reactor, similar to what the Russians have actually flown in Earth orbit. Currently, there are about 30 of them up there. I hope none of them come down anytime soon. But you could put electric propulsion systems on a spacecraft powered by a half a megawatt to a megawatt nuclear reactor and thrust for the 20 years, and you could actually get to this distance that rapidly with an electric propulsion system. Okay, it could be done. We did the cost estimate for this, and it came out to be in the multiple billions of dollars to do this. Really expensive. And then there's all the political issues, and the science team was composed of a lot of people who were vehemently anti-nuclear and just didn't want anything to do with it. And so this was an approach that was deemed technically viable, but for a variety of reasons, we set it aside. So what did that leave? Well, no surprise, duh, for those who've heard me speak before, a solar sail. Now, what is a solar sail? I mentioned this earlier, just very quickly. You won't get much out of these red lights, but you won't get much out of any light, really. What happens when light reflects from a reflective material? Imagine this is like aluminum foil. The light reflecting from that will transfer momentum. Light doesn't have rest mass, but it does have momentum, okay? So as light reflects from it, it will push on it. Just imagine little BBs, little pellets bouncing off of the sail material. So if you have a large, lightweight sail in space out of the atmosphere, and you have continuous sunlight falling on it, or light hitting it, that light's reflecting off of it, and it'll make it move. And we've measured solar photon pressure. Spacecraft in Earth orbit have to adjust for the pressure on their solar arrays, because the sunlight will be pushing on the solar arrays. We know it's real. We know it happens. Turns out the Japanese are flying a solar sail right now. They launched one about 3 years ago. But a solar sail that's deployed very close to the sun would get a big kick from the sunlight and be able to get a speed that would get it to get it out to 250 AU within 20 years of launch. And the sail would be big, but only a little bigger than what we built today. It would have to be about 250 meters on a side, quarter of a kilometer. It's pretty big. But we have built big sails. I was part of a program in the mid-2000s that tested a solar sail in the world's largest vacuum chamber. That's 100 feet across, right there, with the diagonal. The sail was deployed from a box about the size of this. Okay? And that's 20 meters on a side. You can see the shadows of the 4 test engineers down in the front. And by the way, when they were in there, we left the atmosphere in for them. That would have been a bad day if we pumped this down to vacuum. But we did test this in vacuum. This big chamber, we can pump all the air out of it and test the deployment in vacuum. And the company that built that, Lagarde, has been selected by NASA to do a 38 meter by 38 meter test flight in 2015. And it's called Sunjammer, named after an Arthur C. Clarke solar sail short story, named in honor of Sir Arthur C. Clarke. We've also flown in Earth orbit this little puppy right here called NanoSail. And currently there are 2 missions under study, one of which I'm the lead for. It's called NEA Scout. And if we make it through all the reviews, we will fly in 2017. and we'll be taking a solar sail to visit a near-Earth asteroid. And after we rendezvous with that asteroid, if everything's still working, we're going to set sail for the next one, because we never run out of fuel. As long as the spacecraft is operating, we can keep going. All right. So we have, there's another one called Lunar Flashlight that's actually going to take a sail and fly it around the moon. When it goes over the south pole of the moon, the reflected light from the sail is going to shine down in craters. We're going to look down in the craters at the south pole of the moon and see what's there. So these are all under study and are on track. If they make it through the reviews over the next year, we should be flying in a few years. So solar sails are now real. Japan is flying one. It's called Icarus. Terrible name, if you know your mythology. Icarus flew too close to the sun and his wax melted and he died. But I don't think the Japanese thought much about that when they named this Icarus. And they deployed their sail at a trajectory to Venus. And they have been flying this sail for 3.5 years. Flying around the inner solar system near Venus successfully. And yes, I don't know if I put the next picture in there. I did. These are actual photographs of Icarus at Venus. How did they do this? Typical Japanese coolness. They put a small sub-satellite on board, about the size of a coffee can, with a small camera in it, and they said, boom, they kicked it out. It took pictures of the mothership. It's a short distance away. It relayed those pictures to the mothership, which used the high-power transmitter to send the signals back to Earth. So they got pictures of themselves at Venus, flying in the inner solar system. So, yes, I'm insanely jealous of the Japanese and their sails.
Excuse me.
Yes?
Did I read that right, that this foil is 7.5 millimeters thick?
Theirs is very thick. That's thick. That's right. Where is it on here? Where'd you see
Right
it?
above
Last
the
bullet
table.
Yep, that's right. That's right. And the reason their sail is so thick, and ours is a lot thinner, is they embedded solar array photovoltaics in their sail,
Oh.
okay, to generate power.
So it's very thin for a PV cell.
It's thin for a PV cell, but thick for a solar sail, okay? We're talking about 2.5 microns for our sails, okay? So those of you who aren't follically challenged, thinner than a hair, okay? So that's the thickness that we're going to have, but we're going to have separate solar arrays to generate power. The Japanese, and again, I love the coolness of what they did, they steer this sail. Appropriately enough, I'll hold up my book on solar sailing. They steer the sail because they have a coating on here that when you put a voltage across it, it changes the reflectivity of the material. And so a sail that is dark absorbs light rather than reflects it, so it only gets half the momentum of the rest of the sail. So they tip and tilt their sail to tack by changing the reflectivity of the quadrants of the sail. And where it's darker, you don't get as much push, so you get tip and tilt control. And so they control it electrodynamically. They control the attitude of their sail. All of our approaches, in typical American and the Europeans, typically the Germans are doing the same thing, is all mechanical. We change the center of mass versus the center of pressure, and that lets us tip and tilt the sail. But no. None of these moving part stuff to the Japanese. They do it electrodynamically. It's way cool. But the result is their sail's heavy, and it doesn't scale well for really aggressive missions. And we want to go to some pretty aggressive destinations.
Well, when you're far away, the PV value of the sail diminishes.
And that's
You're
right.
not flying near Venus.
But near Venus, it works great.
Yeah.
I mean, it's a very inefficient PV, but they're close to they're at Venus, right? So they get lots of sunlight. So let's talk now about real interstellar travel. I've talked about precursors and how we can go to 250 AU. Okay. But what's real interstellar travel going to be like? Well, first thing you got to do is get rid of your science fictional notions about warp drive and jump gates and going faster than light. We don't know of anything that can really go faster than light. It looks like nature probably prohibits that within what we understand. Warp drive's a neat idea, and it's illustrated down here. This has made a lot of news lately, the Alcubierre drive, which is basically where you have this thing called negative mass, and you have repulsive mass and attractive mass, and put a little black hole in front of you and this repulsive mass behind you and ride the wave. Well, that's all really theoretically very interesting, but we don't know what negative mass is. We don't know how to manipulate gravity to create these black holes, so I'm taking it off my list. Okay? I'm sorry, but for someone who works in my field, I'm considered kind of far out based on what I'm going to tell you now, but I'm not so far out to invent new physics. So we're gonna have to eliminate those. So I'm going to be grounded in what we understand about the universe today. Now, admittedly, we may be all wrong. Okay? And there's a part of me that hopes we're all wrong. Because I would love for nature to have left us a loophole that lets us go to the stars faster than it looks like we'll be able to do it.
But Les,
Yes.
you're not wrong.
Well, I hope I'm wrong. But within what I'm going to talk about, it's not impossible. Nature has not told us it's impossible to go to the stars. Nature has said it's really, really hard. Okay? But not impossible for us to go to the stars. If we ever have to get off planet, did anybody see this series on Nat Geo channel? Okay? Something's coming into the solar system. Life on Earth will end in 75 years.
Galactus.
Go. Okay, what do? Well, I was actually asked to consult on this show, and they asked me what approaches we would use to get off planet, and there are lots of approaches. But the one I said that was the only workable, in my opinion, realizable thing we can conceivably do with a Manhattan and Apollo project combined on steroids for 75 years is something called Project Orion.
Oh, yeah, that one.
It's the only one I think we can do in that short a time frame. Okay? So, Project Orion. What is this? Take your ship that retrieved Apollo 8, take an aircraft carrier, put it here, put pusher plates the size of multiple city blocks underneath it with huge shock absorbers. If you want to know the scale of the shock absorbers, go to Tokyo. Anybody been to Tokyo? Anybody here? Have you been to the Tokyo Edo Museum?
No.
Okay? In Tokyo, they have their museum, the City History Museum of Tokyo. Tokyo's an earthquake region. They don't want their museum destroyed in an earthquake. So they built their museum on these enormous shock absorbers. Okay? So when an earthquake comes, the museum is the place to go. All right? Because it's going to ride out that earthquake on these incredible shock absorbers that they have this building built on. Well, this is the kind of thing you're going to put on the pusher plate and your aircraft carrier, and you're going to start setting off small fusion devices underneath you. And you're going to ride the wave to get from the Earth into space and get to a significant fraction of the speed of light.
It's a sustained rocket jump for those of you who play video games.
There is, the studies were done. There was actually testing done with non-nuclear test articles of using pusher plates and explosives paste to propel a vehicle. And if you do you get 1 G by exploding 1 nuclear bomb every 3 seconds behind the vehicle for a long time. Okay? And you get up to about 3% of the speed of light, that's 140 years to Alpha Centauri. Of course, you trash the planet in the process, but you know, if the Earth's going to be destroyed in 75 years, I think I'd start building a fleet of Orions. And I'd be taking my chances. Right?
And hope nobody leaves early.
Yep. What's that?
And hope nobody leaves early.
Well, hope the guys who figured out this thing was going to hit the planet were right. Right? You know, you don't want to trash it. But the point is, guys and ladies, and everybody here, we could do this if we didn't have to worry about the consequences, right? Now I can ask, why don't we do this today and just put it all into space and do it from out in space? Well, you have to lift all that mass. And that's really, really hard. Okay? And then you get all the political problems of, hey, yeah, we're going to build these bombs to go.
The real problem is not lifting the mass. The real problem is having a 100% failure-proof lift technology that never crashes back.
And no one steals it.
Details, right?
How far away would you have to start for it to not destroy the Earth behind you?
I mean, you'd have to be starting from space before you started the explosions
Outside
on the
the
pusher
solar
plates. No, just off the Earth. You want to do it well out of the atmosphere so you don't produce EMP or things like that, but a high Earth orbit, you could probably start there.
As long as the ejectors are not in a capture orbit, the fallout's not going to hit the Earth.
You worry about other things, the damage to satellites, electromagnetic pulse, you got all kinds of issues you want to worry about. But I think it's mainly get out. But then you lose one of the big advantages of this, and that big advantage of this is how you get really massive things off the planet and into space. And it's the energy of the bombs to do that. So the bottom line is we could do it. It's just, you know, would we ever really want to do it?
Is there enough uranium on Earth?
Yes. The studies have been done. There have been system studies. There have been people who've actually looked at how you would do this. Okay? They do it for fun.
What year did Orion start originally?
That was in the 50s.
Yeah.
And it terminated at about the time, it wasn't terminated, I think, till the mid to late 60s.
Yeah, it went on for quite a while. Like Freeman Dyson, the physicist, was involved in Orion. He was
That's
one
right.
of the PIs in it.
And there's a great book out there called Project Orion, where they interviewed Freeman Dyson and a lot of the folks who worked on this. and documented a lot. There's a YouTube video that you can go see where they actually did non-nuclear testing out in the desert with vehicles to look at the dynamics of the flight for these things. So, being Oak Ridge, got to talk nuclear. Nuclear fusion propulsion. Fusion has the energy it would take to go to the stars, in theory. But in order to use fusion on a spacecraft to produce power to drive your ship, you've got to get to the point where you have a very small, compact fusion power source where you can, unlike today, get more power out than you put in, right? So today, we're able to achieve fusion reactions on the planet outside of fusion bombs in these big chambers where a lot of power is used to confine the particles and compress them to get the atoms to fuse to produce energy. But we're still not getting more energy out than we put in. We haven't achieved break-even yet. As soon as we do that, we've got to start miniaturizing and getting it small enough to fit on a spacecraft. Nonetheless, if you postulate that you can have a reasonable-sized fusion drive, and you know then about how much fuel it would take, which isotopes of helium you're going to use, and what kind of protons you're going to use, and if you have to catalyze it with helium-3, and all the different things that go into that. There are people who've done designs of spacecraft going all the way back to the 70s, Daedalus spacecraft, to do this, to go to the stars, to go to the nearest stars. And you can see here, in comparison to the Saturn V, how big a fusion-driven starship would have to be, assuming you can get a compact fusion power source.
Your caption says fission there.
It should not.
Yeah, okay, that's what I thought. The main drive is.
It is fusion.
Did they have a fission drive on the thing's subsidiary? I've forgotten.
I don't remember that. I don't believe they did.
I don't think they did.
That is a typo.
Yeah, no, that's fair enough. I just was kind of curious if they had a second energy source labeled.
Look at these fuel tanks. Oh my gosh, this thing is huge.
And by
You're
the
getting
way,
the impression interstellar travel requires something big.
by the way, those fuel tanks were filled with helium-3, which would require probably mining the gaseous outskirts of Jupiter to get that much helium-3.
The numbers. 54,000 tons, 450 tons as payload, 36,000 kilometers per second to Barnard Star. Yep, there's the 30,000 tons of helium. It's a 50-year travel time. It's not bad.
Assuming it doesn't hit anything.
Those are other issues.
No, but they're relevant, though.
They are relevant, but you're right. There are a lot of issues with people surviving the speeds and what impact with dust grains traveling at a substantial fraction of the speed of light is like hitting a boulder. The radiation effects from colliding with even interstellar hydrogen. It's like being in a particle accelerator and getting irradiated. So there are lots and lots of issues that have to be solved before we can do this. I'm focusing on the propulsion element of it. Antimatter propulsion. You know, antimatter is real. It's not just in Star Trek. It's produced as a matter of course in particle accelerators. At CERN, over in Europe, and they collide these protons traveling at high speed and they smash them up and see what comes out. Some of the things that come out are positive electrons and negative protons.
The spallation,
Positrons and...
the spallation generator here for neutrons at Oak Ridge generates a whole lot of antimatter as part of the process.
And antimatter is interesting because it basically looks like normal matter, but it has an opposite charge of what you would expect, and one of its spin states is different. And the neat thing about it is, it's charged particles typically. Not all antimatter has a charge, but these do. And that means that you can trap it in a magnetic field, right? Charged particles can get trapped on magnetic field lines. So there have been people that have built vacuum containment systems, get all the air out, have vacuum, a strong magnetic field. You ought to be able to trap antimatter in the vacuum and not have it hit other matter and annihilate, which is what happens. Best energy conversion we know equals mc squared, a proton and antiproton. It's the most efficient conversion into energy that we know of, okay? So if you can trap antimatter, though, then you have an incredible power source for an interstellar ship. Got to tell a side story. There was going to be at Marshall, 10 years ago, an attempt to build the world's first antimatter thruster. And they built a containment vessel that was going to be a strong magnetic field in vacuum. It was over in the Propulsion Research Lab. And the thinking was they were going to drive up to the Fermilab Accelerator in Illinois, attach to the beamline, and they were going to divert through magnetic fields some of the antimatter into this trap, and then put it on the back of a truck and bring it to Huntsville. Okay? Now, the amount of antimatter contained in this vacuum bottle, you know, yeah, it is funny, right? But the amount would be, if you had a total failure of containment, it would be like getting a dental x-ray. It's not much antimatter, okay? I mean, just, you know, the total global production of antimatter is on the order of nanograms, and this is a small fraction of a nanogram, right? So it was going to be trucked back, but they were thinking, you know, we probably ought to tell somebody we're going to be carrying antimatter on the highway. So they said we probably need to, you know, even if it is just a dental X-ray, there are rules for hauling radioactive
We don't have a
materials,
placard for
right?
that. That's what they said.
Yeah, you should have been in some of the discussions. We better do this. And so what they did is they put together a plan, and they went to the it was a National Transportation Safety Board, whoever it is that governs the rules for carrying radioactive material around, right? And they said, we want to truck some antimatter back from Fermilab back to Huntsville. So, you know, I'm a government worker, so I'm used to jokes about bureaucrats, and it's okay for me to talk about bureaucrats. So the bureaucrat they went to talk to said, let me see. Oh, yes, we have an existing specification for that. What? Okay. Turns out they did. Here's what you have to do to transport antimatter across state. They had it. So the only thing we could figure is that back during the heyday of the Cold War, people were looking at antimatter bombs. All right, that's the only thing I could figure, and that these regs came about from somebody having thought about this a long time before we did. Well, unfortunately, the funding for that project was terminated, and they didn't actually do it. But it would have been way cool to have built the world's first antimatter thruster. It would have been just basically little mouse farts in terms of thrust, but it would have been way cool and would have been an interesting project to write about, right? But we didn't get to do it. So, if you want to use antimatter to go to the stars, what do you have to do? Well, you have to have a lot of it. Okay? So, if you want to go to another star and get decent trip times, 10 to 100 years, between 4 and 40 light years, you need 1,000 tons of antimatter.
1,000 tons.
Global antimatter production, nanograms. Got to get up to kilograms. Got to get up to thousands of kilograms. We're not going to do this on planet. This is huge. It's not safe, and we're going to have to find some more efficient way to produce antimatter. So, fusion hasn't achieved break-even. We don't know if we can get there, and if we get break-even, we have to miniaturize it. You have to build something that makes the Saturn V look like a toy. If you're going to go with antimatter, you've got to develop tons of antimatter. Now we get to the extension of solar sails. So what would you have to do to take this solar sail that we're going to go maybe to the interstellar probe in 250 astronomical units and turn that into a real interstellar craft? Well, the first thing you have to think about is size. In order to build a sail that could go to another star, and there are variations on this, what we determined is that you would have to have a very large sail, think the surface area of Alabama and Mississippi combined, deployed close to the sun, and about 10 to 100 times thinner than the current sails we have today. Okay? So, is there any fundamental physical reason that says we can't do this? No. But my material science colleagues probably want to throttle me. Because what material is this made out of? How are you going to deploy it? How are you going to control it? Those kinds of issues. Now, if you want to have a smaller sail that doesn't rely just on sunlight, a solar sail, there is another way to do it. What you can do is you can put a laser in space, or a maser, focus the energy on the sail, and continue to push it long after the sunlight falls off. Right? So instead of the decreasing thrust you get as you move away from the sun, what you do is you take the laser or the maser, you can do a microwave sail, and you focus it on the sail and keep pushing it to accelerate it. Well, it turns out you can get your sail size down dramatically. You can get it down to just tens of kilometers versus hundreds of kilometers, okay? But the laser power is roughly equivalent to the energy output of humanity today.
Yeah,
Okay? So, we're not there yet.
not practical.
Not practical today. Now, I would contend that all of these concepts that I've outlined for you tonight, all except Orion, are not things that we can envision doing today because we don't have the engineering capability to do it. But if we're to become a civilization that are masters of our solar system, if we have space solar power stations beaming greenhouse gas emission-free power down to the surface of the planet, we're mining the asteroids, which are what companies are saying they want to start doing now. We have bases on Mars, and we're manipulating and living and working as a routine thing within the inner solar system. And we are on a trajectory to do that. And if the rate of progress in our ability to generate power and use power continues on its current trend, as it has been, within just a few hundred years, we should be in a position to be able to engineer things of the scale I'm talking about here to go to another star.
500 years.
Could be. I don't know what the time frame is. It's certainly not 100 years. 200, 300 to be where I would put it, but we don't know about breakthroughs. We also don't know if the trend of technology and progress is continue, or if we have a downward slope for a few centuries. We don't know.
We also don't know what other obstacles there are.
Absolutely. Again, this talk is centered primarily on
Well, the obstacle
point of
propulsion
view.
is the first obstacle to get past, and then there might be others.
The point being is that it's laughable from a term of how do you do it engineering-wise, but there's no fundamental reason it can't be done. And if you're a person who looks out at all these planets that are out there, and you start thinking about the question of, well, wait a minute, this is a big universe, are we alone? Right? Is there somebody else out there? You know, has somebody else figured out how to do this? Are they out there doing this somewhere? Are we eventually going to get there ourselves? I don't know. Somebody had a comment here.
I was just wondering, so in that previous slide, are you talking about the laser traveling with the sail?
No. The laser is in orbit around the sun. You might have more than one.
It's a synthetic sun.
And you take the energy from the sun to power the laser to focus it on the sail. And to keep it focused on the sail, this is, I have to give credit to Dr. Robert Forward, who came up with this and published it the first time. Even a laser is going to diverge, has divergence. It's still a point source, so it's still going to diverge. So out around Jupiter, you've got to put a Fresnel lens that's 100 kilometers in diameter and shine through that Fresnel lens to refocus it to keep it on the sail.
Just don't miss.
Don't miss. But what's neat is there have been experiments done in microwave levitation of lightweight carbon fiber sails where they looked at the geometry of the carbon fiber. And if you build a sail out of some of these materials, it will stay on the centroid of the beam.
What they do is they circularly polarize the microwave beam so that you're not only imparting linear momentum for acceleration, you're imparting angular momentum.
And so if the
Spin like a
beam
football.
wanders and you can't point it exactly, you don't have to worry about it going off the sail and the sail getting lost.
cool.
The sail will ride the centroid of the beam.
You're making the sail into a gyroscope.
And so
Yes,
it's
that's exactly
essentially
what
yes,
you can.
and it'll stay on the beam. So there are some serious experiments looking at some of the other issues associated with laser sailing. Yes, sir.
I got here late, sorry. Did I miss you mentioning anything about ion drive?
I did. And that's good for near solar exploration, but it won't have the energy density to get you to the stars. With fission, you probably couldn't carry enough propellant even with a fusion-driven starship to do that. The mass fraction would be too poor.
Unless you can gather things to throw out the back from debris from the front. Like
And like the
Not only
Bazaar
whether that's
ramjet or
actually
something
possible,
like that
yeah.
with fusion drive. So the ion propulsion is good for deep solar system and nearby in the deep space around our solar system. But to get to the stars, you need higher energy density than that. And everything that we've seen and that I've looked at requires something essentially really big. Okay, I was asked to give a TEDx talk in Huntsville about this, and the topic was think big. And you can't think much bigger than this in terms of grand challenges for humanity, of what it would take to go to the stars. So to get to the point where I can wrap up and I can get off stage after an hour, the galaxy looks like it's full of planets. There's a lot out there to see. Nature has not said it's impossible. Nature's left us ways to do it. It's just going to be really, really hard. And so are we as a species up to that challenge? Are we going to take it up and are we going to do this someday? Or are we going to turn our backs on basically spreading humanity to the stars? I don't believe we're going to do that. And so I'm going to close by giving a plug for a workshop that's going to be held here in Oak Ridge in November 2014. It'll be the third Tennessee Valley Interstellar Workshop. And it is a gathering of serious researchers from all over the world, actually. We broadly interpret Tennessee Valley. We have folks flying in from Europe and elsewhere, all over the country to participate in this, although we try to focus mostly on local R&D between Oak Ridge and Huntsville. To talk about the issues of going to the stars, how we might do that, and what we have to be doing in terms of the stepping stones today, things like the interstellar probe that I talked about and other experiments that might enable that to happen someday. So this is going to happen in November. We have a website, tviw.us, if you want to follow the progress of this, and we'll have a call for papers and for participation that'll come out. A shameless plug for one of my books. I edited this book with, it's got original science fiction stories by a lot of pretty well-known science fiction writers, Ben Bova and others. And interspersed with it are the essays of kind of the facts behind the fiction, similar to what I've talked about today. So if anybody's interested, I have copies of those. Questions?
Yeah.
There were two back here.
Yeah.
That's the one you haven't heard, I think. Because one of the things I did this past week, and all of you can see the results if you go to the town website, you'll see a poster about this and about his talk. I've got some outside, I'll go get them, but I worked on one a few years ago, and okay, pretty impressive. This one was different. This one said that he was an advisor. It said you were an advisor on the Europa report.
That's right. I
I
was
think
one of the
that was a
technical advisors for
fantastic
Europa
movie,
report.
and it was so different in the way it was put together from anything I've ever seen. I recommend everybody see it.
It's a good movie.
I think you're very proud of that. And I want to ask you, why was it so different? Wow, it was like when I first saw Alien. Alien was different. Europa report was not spooky. It was just, it was like a documentary.
To me, it was very suspenseful, too.
It was
I
very
mean,
suspenseful.
Incredibly suspenseful. Well, I have to give a caveat. I've consulted on another movie, and it was the new Lost in Space movie, so don't hold that against me.
No, I didn't
Okay?
mention that.
Yeah, I try to forget that, but they ignored me.
Yeah.
But Europa Report, they started at the very beginning saying we want this to be as realistic as possible. Okay? And when I consulted on Lost in Space, they told me, we don't care if it's realistic, we'll do it if we can. And if realism has to suffer for what I want to do as a director, you lose. Okay? I was never told that by any of the producers for Europa Report. They basically said if it's not realistic, we don't want to do it. Okay? And to me, it was like, oh, great. But of course, the nagging fear I had is this is going to be a boring movie, right? Because
No,
typically,
it was fascinating.
drama is typically founded in the things that most people think space travel is, not what the reality of space travel is. Reality of space travel for people is long periods of time with nothing happening, which is a good thing. You don't want excitement on a deep space voyage. You want it to be as boring as possible, right? Because that means everything's working and you don't have any crises. But anyway, the difference was, and what was nice about that, is they wanted everything to be as accurate as possible. And so they told me they were not going to do things that were not accurate if they could help it. And if you're interested in the TVIW and some of the issues that are more than just propulsion, if you've heard of the British Interplanetary Society, the next two issues of their journal, I believe it's the next two, it could be the one after this, but I think it's the next two, are papers that were presented at our workshop in early 2013 in Huntsville.
A year ago.
A year ago. And the two next two issues are the proceedings, essentially. We have peer-reviewed papers in the journal. And we have papers from engineers. We have a paper from an anthropologist, talk about the cultural aspects and what we have to be aware of on these long voyages if it's a world ship and maybe an encounter with other people out there or other whatevers. And serious discussion of the human effects as well as the technologies required to go to the stars. So if you're interested in finding out more about what serious studies we've done, the next two issues of that journal are devoted to our workshop last year. So you can go find that and get copies, probably in the library, or you can buy them online from the British Interplanetary Society. Anything else?
I thought it was someone else having the hand. Someone behind David. I thought I saw a hand. Guess not.
No? All right. Well, thank you very
Yes,
much.
thank you.